Let's spend a little time thinking about the data structures that we sometimes take for granted, and what they're good at and what they're not so good at. One thing that you may not be aware of is that arrays are actually very good at looking up data. If you give an index, an array has this neat capability where if you know the computer knows the location of the start of the array, and if you ask for index 0, it knows to look right at that start, but it also knows how big the data is that's going to fit into each slot in the array, and that all of that data is fit into one window in memory. And so if you ask for the third item, for instance, it can take the starting location, the size of a given item, how big an item is going to be, and then add that size times the index you've asked for. So 2 in the case of the third item. You ask for index 2. Well, it does size of an integer in this example times 2 and looks that far forward. And so it gets very fast lookup. When you give it an index, it can just do some simple math and find the location that index is in memory, because all of an array is stored as one unified chunk. But there are some operations that may be faster or slower because of that structure of being stored as one unified chunk. It also means that arrays have a limited length, which can be another limitation for them. So keeping in mind that arrays have to be this unified chunk, that they typically are kept without empty spaces in them, then we want to think about some of the expenses of doing different operations on an array. So if we had this array here and we wanted to add data in the middle of the array, say we needed to add something between the 6 and the 8, then what would need to be done so that we wouldn't lose data, but that we could add that something between the 6 and the 8? Likewise, what would need to be done to add something at the beginning, before the 2 in our array? And what would need to be done to add something at the end, if we already know where the end of our real data is in the array? What would need to be done to add something there? So those are 3 different operations, all of which are possible in an array, but what needs to actually be done step by step to achieve those? So pause the video for a moment and think about that idea of adding data at these various locations, and what steps would need to be taken to preserve the features and the contents of the array otherwise. Pause a moment and think your own ideas about them. So let's approach these in the order that they were given to us here. If I wanted to add the number 7 to go between the 6 and the 8, for instance, well, I know that I want 7 to be in this slot, but I can't just say index 2 in the array equals 7, or I'll lose the 8, right? It's important to keep the data that was already there. And so here I need to move over the 8. But in order to move over the 8, I would first need to move over the 10. And so to insert that 7, I would have to shift over several values to make space so that the 7 could be inserted without losing either the 8 or the 10. And so that I still have that feature that for an array, the data is all stored in one well-defined chunk there. So to add to the middle, if I know that location where I'm adding, then I would need to shift everyone over to make space for it. And even worse, if I'm adding at the start, let's say I needed to add the number 1 to the start here, well, to add 1 in the start location, I would need to shift 2 over, which would require shifting 6 over, which would require shifting 8 over, which would require shifting 10 over. So I would have to shift over all the other data. So in the middle, shift right any data after insertion index. And at the start, we would have to shift right all existing data. Now, at the far end, if I know the index of that end already, which we're going to assume at the moment, if I knew I was inserting something here, then all I have to do is insert into that location, that index, right? We can just set it equal to that thing. So if I wanted to insert, say, 12 to go into this spot, well, I can just put 12 right into that spot. If I already know the index of something, adding into an array, it's no problem. So thinking in terms of complexity, adding into that single end index, if I know the index, that's one operation. That's O of 1, right? Adding at the start required shifting over all existing data. And so that's O of n, pretty obviously, where n is the size of my existing data. So if this list or if this array grows very large, if it has millions of items in that array, then I'm shifting over millions of items each time I want to insert something at index 0. It's worth noting that array lists are a nice built-in Java class that automatically handles some of these complexities for you, but they don't handle them intelligently all of the time. They will just manually move over everything that needs moved over, and the assumption is that you, the programmer, will think about the complexity of the action you're taking. And if you keep inserting at index 0, then you'll get very, very slow performance from your array list. Now, the middle. This is a good example where we know we have to do some work. Are we in a better complexity class than when we have to do all the work? Are we in as good of a complexity class as when we only have to do one thing? Well, if you think about the example I gave where it was the actual middle, the dead middle of it, that would be moving over 1/2 n items, and therefore it would still be O of n. In fact, inserting at an index other than the empty space or other than some sort of constant number from the end is always going to be O of n. If I said insert something that was 2/3 of the way through, well, that would be moving over 2/3 times n items, and we throw away that coefficient, so it's O of n. So in an array, inserting in that empty index, if I know its location, is fast and useful. Inserting basically anywhere else is not so fast. It's going to take shifting over some data to preserve what was already there in the array. So we're going to look at some other data structures over the next couple of lessons that will help us to think about ways that we might change this picture. We might change the kind of performance that we can get on different operations. One of the things that I hope you take away from this class overall is an ability to select the right algorithm for a particular problem that you're facing, and to select the right data structure to store the information needed to solve a problem that you're facing, or to handle or to create an application that provides some usefulness to people. And so one of the things that we're going to talk about in that context is an abstract data types. And these will often be abbreviated as ADTs. So an abstract data type is a specification of some possible values and some operations that can be done with those values. So an array is actually, it fits a particular data type, an abstract data type, and its possible values are whatever the specified type of the array is and some limited number of them, right? You give it a size and it has that many values. If you say it's of integers, well, the possible values are that many integers. And the operations that can be done are things like looking up by index or assigning something to a particular index. And so we are going to look at other possibilities, other models for data types, that they may not have the same exact specification or operations as an array does. In particular, we're going to look at the abstract data type of a list. And a list typically has a few different features that you'll want to be familiar with as you start into this. So the head of the list is the first element of the list. And likewise, the tail of a list is the last element of a list. Some people will use these to refer to things in an array. For example, the array list follows a list kind of model for things. And so we could talk about the head of an array always being index 0, and the tail of an array always being that last used index in it. So in the original array that was drawn here, the head's value is 2 and the tail's value is 10. Well, we'll keep that idea of the head being the first element and the tail being the last element, and we'll start to stretch to think about, are there other ways that we could build a data structure that has some concept of a first element, a last element, maybe even a next element after the head or a previous element before the tail, and to use different designs to be able to store that kind of list, that kind of linear layout of data that may not be limited to this idea of a solid indexed chunk of memory like an array is. So you're going to be digging further into these ideas of other abstract data types and how a list in particular has a head and a tail. You can typically add and remove things from it, but that the abstract description, it has some start, some finish. We can add and remove things. The abstract description, the abstract data type, really only tells us a general idea, and how we implement it in the background, the specifics of what we use. Do we use an array in the background, or do we use some other way to store information? Well, those will decide the performance and the particular details of our specific operations that real data type, like an array list is a real data type, that real data type will get as you use it. And so you're going to consider these ideas as you look at parts A and B of the lists activity today.